As we continue the proceedings this afternoon, we are going to discuss now unsupervised learning, which I mentioned only very briefly during the introductory lecture from this morning. Okay. Using the 100 most common words in the English language, I would describe unsupervised learning as learning information without class names, or alternatively, finding hidden breaks between groups. Okay. If we expand our vocabulary slightly, then perhaps you could even extend these definitions to the search for underlying structure within data, or learning from data without rewards or labels. These are all sort of apt descriptions of unsupervised learning. What follows in this lecture is going to be a very broad overview of many of the common techniques that constitute unsupervised learning. I'm going to start with a very familiar example. And if you are about to roll your eyes, I apologize. You may want to keep your eyelids down so they don't get stuck. But suppose nature produces some family of sources that tend to be either big or small. So mathematically, we could represent this distribution of sources as something like the probability is 0.35 multiplied by a normal distribution centered at 30 plus 0.65 multiplied by a normal distribution at 60, where n is the normal distribution. Okay. So using NP-random, we can generate samples from this distribution. So we can execute this cell. Essentially, in this instance, we're just defining a bunch of random sources distributed according to that formula we showed a second ago. So we use a random number generator to figure out whether or not we have something from the small population or the large population, and then we draw from the appropriate random distribution there. Okay, so in practice, right, we observe nature. We do not actually know the true underlying probability density function for the sources that we care about. Okay, so again, protect your eyes if you are apt to rule them. But this brings us to our first example of unsupervised learning, okay, density estimation, which is most commonly done with histograms. Okay, I paused in order to allow you all to roll your eyes. Adam, please shut up. Please stop telling us about histograms. Nevertheless, a histogram is actually a form of unsupervised learning. We're trying to estimate what is the PDF for some data for which we have made observations, right? So let's assume we've measured the size of 100 sources from the aforementioned big and small, whatever the thing is that's made in nature, right? The PDF can be estimated with a histogram, right? So we're going to generate 100 random samples from that function that we had a moment ago. And then we're going to just plot a histogram of what we get, okay? And so here's a common standard run-of-the-mill histogram showing the estimator or an estimation of the PDF for this distribution. This is actually unsupervised machine learning. Okay, it's not particularly complex, but this is unsupervised machine learning, right? I'm not going to spend a whole lot of time belaboring the point about histograms. I think I've done that enough already within the DSFP. But I do want to quickly remind you that if you're thinking about problems where you have to make something like a density estimation, that kernel density estimation or KDE methods are a very nice alternative to histograms. And we can actually illustrate, again, for this same data set, what a KDE looks like. In this case, we're just using a Gaussian KDE. So we have a Gaussian of small fixed width, and we're gonna basically just stack Gaussians at the location of every random source within our sample, okay? And when we do that, oh, and this is the thing that always happens where I can't scroll. Okay,
Adam, well, you can Adam, if you hit that blue thing that looks like a power button, now you'll be able to scroll, or maybe not. All right, my turn to not say things.
I always forget why this happens. But at any rate, you can see the most of the KDE here. What you don't see at the bottom, if you run this lecture in your own notebook, you'll see at the bottom is just all of the individual small Gaussians, basically. And then the thick line here, or the KDE, is just the summation of those individual kernel elements, which is a Gaussian. Okay, and we see a smooth representation of the PDF here. One very nice aspect of KDE is that it generalizes to multiple dimensions in a fairly straightforward fashion. So using algorithms that are commonly available in Python, you can easily build a KDE for 2 dimensions, 3 dimensions, 4 dimensions, 5 dimensions. I do want to quickly mention that we should all beware the curse of dimensionality when it comes to techniques like for density estimation, in particular things like KDE, but also just generically for any sort of unsupervised application. Briefly, the curse of dimensionality is that high dimensional data sets are inherently sparse, right? If you have a whole bunch of dimensions, you have many, many different axes upon which to describe your data. The relative distance between samples within your data becomes larger and larger. So if you have many, many, many dimensions, and many in this case can mean tens, hundreds, thousands, millions, we will see models where there can be millions of parameters before the week is over. All samples become relatively equidistant. And so looking for a cluster or trying to find some region of high density is very difficult, okay? And we actually can demonstrate this pretty easily by drawing 10 random points from a standard multivariate normal, and then measure the distance between the 2 closest points within that space. Okay, so here we're going to say n samples is equal to 10, and then we're going to randomly make a multivariate normal that's 2-dimensional, 3-dimensional, 10, 100, and 1,000 dimensional. And then we'll do a quick loop after we draw these random data points to figure out what is the closest separation in that multidimensional space between any 2 points. And we'll then look at how the separation changes as a function of how many dimensions we have. Okay, and it's a pretty quick calculation, but you can see that in 2 dimensions, 3 dimensions, right, the distance between points is relatively small. By the time we get to 1,000 dimensions, right, the minimum separation between the 2 closest points, 10 points in this 1,000-dimensional space, is 42, right? Orders of magnitude higher. So this is an illustration of the curse of dimensionality. In the end, all that I am really saying right now is that don't, run out and start using KDE to find high density regions in a 100-dimensional space or 1,000-dimensional space. Okay. All that being said, unsupervised learning, another method of unsupervised learning, can help with the curse of dimensionality. And this is with a family of techniques that are called dimensionality reduction. Okay. This is not the focus of today's lecture. I'm going to mention a couple quick methods. I'm not going to show the underlying mathematics, but these are things that often show up in the astrophysical literature. So that's why I want to quickly cover them today. So a very common and one of the sort of best first methods for dimensionality reduction is known as principal component analysis. And PCA is the linear combination of variables that provide the maximum variability within a data set. Or in other words, I think this figure illustrates things somewhat well. PCA aims to use techniques from linear algebra, essentially the search for eigenvectors, to define a direction of maximum variance. So here we see a data set that lives in 3 dimensions, and unlike the orthogonal basis that is initially used to describe the data, the x, y, and z axes, if we have a projection along what's shown here as a blue line, okay, that blue line is actually what would be called the principal component, or the direction that explains most of the variance that is present within this data set. Okay. After you have found this principal component, additional components are found that are orthogonal to this original direction. And so in this case, that's shown as a gray plane, which is orthogonal to the principal component. And the next component is called the second principal component, and the third principal component. This was only a 3-dimensional set, so we could only find 3 principal components, but this is how PCA works, essentially, trying to find directions of maximum variance. And in this way, it's often the case in many data sets that with just a few components, on the order of 2, 3, maybe as many as 10, a substantial fraction of the variance that is present within a data set can be explained. But this depends on the data set in question, right? In the literature of late, PCA has become a lot less popular. I think there's a few reasons for this. One is that PCA is scale dependent. So if you've got some feature that varies from 0 to 1, and you have some other feature that varies from -500 to 500, the latter will be determined to be more important in your PCA projection. But I think more importantly, it is rarely the case, or is often not the case, that an orthogonal basis can truly describe the variance that is present within a data set. So imagine for a moment if you just have a data set that lives on the surface of a sphere, okay? On the surface of a sphere, you actually cannot define any sort of principal direction, right, for your first component, from which you will then define a whole bunch of orthogonal components from that. Okay, so it is, I would say, because a lot of data sets are complex and they don't live in linearly separable data spaces, surfaces, that PCA has become less popular of late. More recently, a very exciting method that many use is called T-distributed stochastic neighbor embedding. And I'm going to explain this to you the way one of my good statistician friends explained it to me. TSNE is magic. So again, I'm not going to get into the mathematics, but in brief, okay, the very hand-wavy explanation, if you want to do dimensionality reduction with TSNE, is that TSNE finds a low dimensional projection of the high dimensional data, where in the low dimensional projection, small and large distances from the high dimensional space are preserved, okay? So in other words, what this means is that if you have some very, very complex space upon which the data live, by the time you've projected it down to 2, 3, 4 dimensions using TSNE, all of the small local distances will be preserved in that projection, while the large distances will be spread out. And this is an example from scikit-learn. It's a common example for clustering and classification problems, but this is a clustering, or sorry, I should say a dimensionality reduction, excuse me, of the handwritten digits data set that's available with scikit-learn. And you can see that in this 2-dimensional projection, and these images are 8 by 8 images. So essentially these are 2D images with 64 features, one measure of brightness in every pixel within the 8 by 8 image. Okay, so reducing this 64-dimensional data space down to 2 dimensions, you can see that almost all of the numbers, 0 through 5, are clustered separately, okay? With small local distances between things that are the same and large separations between things that are very different. Okay, so TSNE is a great tool. Speaking very quickly about PCA and TSNE, one thing that is worth remembering is that PCA is deterministic. So every time you run PCA to do dimensionality reduction, you will get the same results. TSNE is not. So if you use exact same inputs for TSNE and you run it, and then you run it again on the exact same data, you may get a slightly different projection the second time around. Okay, clustering. This is what I want to focus on today. This is the big thing that I want to look at. And when I think about unsupervised learning, I typically think of clustering and not these other techniques that I've mentioned, although they, again, are all part of unsupervised learning. All right. So a cluster, when you're looking in a multidimensional data space, is a collection of objects that are all similar while also being dissimilar to other objects. So thinking back to that figure we had a moment ago, right? All of the number ones are kind of similar, but they're also clearly different from the number 0, right? There are many, many machine learning methods that can be used to search for clusters within a multidimensional feature space. In fact, there are so many that there's no way I could possibly describe all of them or even a substantial fraction of them during the lecture today. Okay? So instead, I'm going to talk about a couple of the very famous algorithms. They are not, I would say, the most powerful algorithms that are available at this point in time for clustering, but they're very useful to understand both from a historical standpoint and also in terms of developing your intuition for how clustering works. So the sort of starting point for all clustering, anyone that wants to do clustering, is a classic algorithm called K-means. Okay? This is always the starting place. And K-means is a pretty simple and straightforward way to identify clusters within a data set. All the user has to do, if you want to run a K-means clustering algorithm, is to specify how many clusters you want to search for in the data, K. So that's what the K stands for in K-means. And then from there, the algorithm will proceed to divide the feature space and find the aforementioned clusters accordingly. Okay. The pseudocode is the following. So you start by choosing how many clusters you'd like to search for. This could be 2, 3, 100, whatever. Then K random sources are selected from the data set. So if K equals 3, we just randomly pick 3 sources within the data set, and we say, okay, to start, the position of these 3 sources correspond to our initial cluster centers. Okay? We then assign each source, every source within the data set, to the cluster center that it is closest to. So you just have to measure a whole bunch of distances, right? And the minimum distance between a cluster center and a source determines what cluster a source belongs to. We then update the position of the cluster centers based on all of the sources that are within that cluster. And that is done by taking a mean. So we just take the mean position of all in-cluster sources, right? And we repeat steps 3 and 4 iteratively until we reach some stopping criterion. And there's many different stopping criteria that could be used. You could say, just do it 100 times, do it 1,000 times, do it 1,000,000 times. You could say, keep going until the change in the mean cluster position is relatively small within some small fraction, whatever. But you just iteratively update like this. Right, so we can see what this looks like, all right, by going through some updates of clusters that we simulate in a 2-dimensional space, okay? All right, so here I have a little bit of code. We're gonna make some data, so X and Y. This make blobs function is from scikit-learn, and it will just create a random data set where you have different multivariate Gaussian distributions for your different classes, okay? And then we're going to illustrate how K-means works by showing all of the data and then picking 3 sources. In this case, we're just going to pick the first 3 sources and plotting them in the 2-dimensional data space that we have. Okay. All right. So here we see that we have a whole bunch of data in a 2-dimensional data space, and we have 3 cluster centers, right? That's what these large X's are here, right? So now that we have these cluster centers, we're just going to figure out, okay, these points are closest to this cluster center, so they belong to this cluster. So we're going to figure out which cluster everything belongs to. All right, I am going to exit the slideshow view so that we can actually look at these figures. My apologies that this isn't working as planned. Okay, so we can now see that we have assigned individual points to the cluster center that is closest. So we will update the cluster centers by taking the average position of the different cluster members here and assigning that as the new cluster center. So in this new figure, you can see that we have new cluster centers, all right, which are the positions in bold, and the previous cluster centers are shown with alpha. So we can see how the cluster centers have moved here. And we've also colored the points once again to show which ones correspond to the new cluster centers that we have. Okay, we will repeat this again. Okay, and again, we can see how the cluster center has moved. All right, so for this cluster down here, it hasn't moved much. The cluster center is still moving here. We can repeat this iteration once again. Okay, again, we see the cluster centers moving. All right, and we'll now fast forward. We'll iteratively repeat this 100 times. Okay, and we can see here that the cluster centers have now more or less converged, right? So the points in purple are one cluster, the points in turquoise are another cluster, and the points in yellow are yet another cluster. Okay? So this is how the K-means algorithm works. Okay. Now, for this extremely simple example, right, we can see that the clusters have converged. Under the hood, there are some user-defined parameters. So we keep saying distance, but you actually have to define how you want to measure the distance. The standard method is typically Euclidean, okay, but there are other choices that you could use. But despite all these sort of under the hood tuning parameters that can be used, there's one choice that really, really matters if you're building a K-means clustering model. And that is K, right? The whole algorithm is built on a user-specified number of clusters, right? We generated the data that we used for the previous example. So we knew that K equals 3, right? But if you actually have some new data set that you're looking at, you're trying to find clusters within that data, the fact of the matter is you will have no idea what K is, right? There's no way to know. That's why you're performing clustering in the first place. But nevertheless, and this is a downside of K-means, by definition, because you have to input some number K, you will always find K clusters, right? Whether or not there are K clusters that are actually present. So many clustering methods require that the user specifies the number of clusters. It's not just K-means, okay? What I don't like about this, me personally, is that there's no natural metric for basically going in after the fact and saying, okay, I've now optimized this function that tells me, yes, for this problem, K should be 5, right? 5 is the number of clusters I should have. Fortunately, there are some other methods that do not require the pre-specification of a number of clusters. Okay? And I think one of the most famous algorithms, again, historical algorithm that has been around for a while, is dbscan. So the way dbscan works is it searches for clusters using a user-specified radius epsilon, essentially how close are individual points to each other, okay? So the way this algorithm works, the pseudocode is, for every source, the number of other sources that are within a distance epsilon are counted, okay? So if you have a source where it has n neighbors within epsilon, and the number of neighbors is greater than some user-specified value, min points, then those sources are considered core points, okay? So the user specifies the minimum number of points to become a core point, and epsilon, the separation between points to be tested, okay? If a source has less than min points neighbors, okay, but at least one of its neighbors is a core point, then that source is considered reachable and it's considered part of a cluster, okay? And then finally, dbscan introduces a new notion, which is that all sources that are not reachable by another core point within the user-specified distance epsilon are considered outliers. So essentially, dbscan searches for clusters within the data, and then individual sources that are very largely separated from other sources within the data set are then flagged as outliers. Okay. So here is a diagram sketching what this looks like. Right? So here we have several points. All of the points shown in red, okay, have at least 2 neighbors within the user-specified radius, which is shown by the various circles which are centered on each of the individual data points here, okay? And so you can see that towards the center of the cluster, all of these red points have 2 neighbors within the specified radius. Okay? Then towards the outskirts of the data, there is a point labeled B, and there's a point labeled C. And each of those points have neighbors, but they only have one neighbor within the specified radius epsilon. So points B and C are also part of the cluster in this case, but they're not considered core points for what it's worth. And then finally, isolated in the upper portion of this diagram is a point shown in blue and labeled N. And the point N has no neighbors within the specified radius epsilon. So that point is considered an outlier. Okay. Working with the simulated data, okay, we can, so, okay, we can resize slightly. All right, here we go. So working with the simulated data, right, you can see in this instance what dbscan finds for the clusters that we had previously found with Kmeans. And so you can see here that the points that are relatively isolated, okay, are labeled as outliers, whereas we otherwise find one cluster here, and then the two clusters up here are actually combined based on the specification of the epsilon, which was set equal to 1 in this example, and the minimum number of samples, which was set equal to 10 in this case. Okay. All right, so as I just said, we see that there are two clusters that are identified. But similar to K-means, there is no metric, unfortunately. We can't say, oh, this is definitely the right number of clusters, or this is the right number for epsilon, this is the right number for the minimum points. So ultimately, right, if we didn't know that this was a data set with 3 clusters in it, we actually wouldn't know whether or not what we just got from dbscan was any better or worse than what we were able to get out of K-means. Okay, all right. dbscan introduces the last component of unsupervised learning that I want to talk about today, which is anomaly detection. Okay, so anomaly detection is a topic of great interest in astronomy. As I said earlier today, a lot of the history of astronomy is point a telescope in some new direction, find something that no one has ever seen before, and then try to figure out what that thing is, right? And this is, of course, an area of great interest for the Rubin Observatory. What if there are undiscovered galaxy subtypes out there, right? What if there is a type 3 supernova, something that no one has ever seen, an explosion no one's ever seen? Or, right, another way that anomalies can present themselves is, what if we don't understand the systematics in the Rubin observing system, right? All of these are questions that can be answered by a search for and detection of anomalies within the data set, okay? How do we identify anomalies? There are many different potential algorithms and methods, and we're actually going to touch on this a bit more later in the week. So instead of talking about specific algorithms, I just want to talk about some of the types of outliers that might be worthy of extra attention should you spot them within the data, okay? So there can be global outliers. And again, I have to resize real quick, but hopefully you can then see everything, right? So here's an example of a global outlier. We have a clear trend within our data, and then a point that is not discrepant solely in its value of X or Y. Other data points have those values, but it is discrepant when looking at the relationship between X and Y. Okay. There's also contextual outliers, okay? So here is case counts of the flu as a function of time, right, on a familiar axis like in the United States. And you can see that it's not unusual for the number of flu cases to go to 0. That happens approximately every single summer. But around the new year in 2021, the number of new flu cases was very close to 0. And this is, of course, because many people were enacting social distancing measures. And so transmission of the flu really, really plummeted. And so it's not unusual that the value is 0. It's just unusual that the value was 0 in the middle of winter. Okay, all right. And finally, local outliers are unusual relative to a particular grouping of the data. So here is an example, right, of a local outlier. We have some areas of high density, and then we have an observation here, which is significantly offset from the regions of high density. Okay. All right, and then finally, label outliers are unusual relative to their assigned class. Okay, so here we have 2 clusters right? Within the data, we have a cluster here at very negative values, a cluster here that's closer to 0, but one member of this class, for whatever reason, has a value that is more or less consistent with being part of the other class, right? So this is something that we might call a label outlier. The detection and identification of anomalies can lead to exciting new discoveries, right? The sort of search and follow-up of anomalies is how quasars were initially discovered. Very famously and recently, there's Boyajian star. And so anomalies are a very exciting aspect and way to look at and search through astronomical data. That being said, I will also note that the systematic identification of anomalies is quite difficult. And in most data sets, the population of outliers that you will find are likely to be caused by telescope artifacts. Okay, so I'll just tell you that while this is all very exciting work, it is hard work. I just want to caution before you sort of run off and start trying to apply anomaly detection to every survey that you may be working on, okay? All right, so in conclusion, I just want to say that, I've just finished a lecture on unsupervised learning, but I do have to confess, I am not a huge fan of supervised learning. It is not my favorite method within the machine learning umbrella. And I've hinted at this throughout the lecture. Perhaps I haven't hid this fact at all, but the main reason I feel this way is that there's no way to know if you've performed some clustering algorithm, how accurate your clusters are, how well you've actually done to identify clusters, right? Is K 7 or should it have been 6 or maybe 8, right? Or if you aren't using Kmeans, if you're using dbscan or some other derivative of dbscan, if you double the number of min points, does that change the clusters? Does that change the clusters to better or more accurately reflect what is actually seen in nature? Right? I don't know. No one knows. There is no actual way to measure this. Well, that's not entirely fair. There is one way to measure this, which is to then go out and collect additional data on the sources in the clusters that you have found, okay? But typically this follow-up, that act, getting that additional data, is the truly, truly hard part. And so if you've been searching for clusters, you've basically just delayed getting to the hard part, which you still have to do anyway, okay? Furthermore, I will note, and if anyone in the audience knows of a counterexample, I please encourage you to share that with the group. But I'm not aware of any truly groundbreaking problems that were intractable. So just basically, here's a problem, but we have no idea how to solve it. And then the application of unsupervised or clustering methods suddenly sort of broke open the problem and made it possible for the community to make progress. Okay. All right, so all of that being said, all right, to be fair, unsupervised learning is still very useful in certain contexts. If you're doing exploratory analysis or you're trying to visualize very high dimensional data sets, okay, density estimation and dimensionality reduction are both very, very useful tools. So, right, I don't need to belabor the fact that even something as simple as building a histogram can provide a lot of useful visual information about a data set that you otherwise know very little about. Unsupervised learning can also be very useful in semi-supervised contexts. So if you have tons and tons and tons and tons of unlabeled data, right? So many, many unlabeled sources with a very small number of labeled sources, it can be possible to perform unsupervised learning and then examine where the labeled sources are in order to understand clusters that may be present or may be able to teased out within the data. And this is what's referred to as semi-supervised learning. And then finally, unsupervised learning can be very useful when you are dealing with something like a live supervised model. So typically, if a machine learning model is built, it will be trained on some subset of the data. It will be very good at classifying things that look like the subset of the data for which the model was trained, but in live applications. So imagine you work at a credit card company, you're trying to detect fraud, or you work for the Rubin Observatory and you're trying to find new asteroids. As you are running a model live on real data, it is often the case that there are examples that show up that were not present within the training set. And as you find more and more of these basically poorly classified examples, unsupervised methods can sometimes be useful to identify new emerging classes within the data. So again, to go back to the fraud example, suppose someone had technology so that the magnetic bar on a credit card could be spoofed quite easily, and machine learning started to catch all of those instances. Well, now maybe fraudsters figure out a way to spoof the chip that is present within a credit card, right? But there's no examples of that in the machine learning model. So you have to use unsupervised methods to see, oh, there's something that's breaking our fraud model consistently in the same way. Okay, so thus concludes my lecture on unsupervised learning.